let's do some geometric operations with vectors.
Right, so on to 3B.1. In the past, if you had a question like this, where a runner runs east for 4 kilometres and south for 2 kilometres, and you're asked how far is she from her starting point and in what direction. So how far, that's x along here. What techniques would you use to solve that in the past? A right angled triangle? Probably Pythagoras. That would help you to find that x value. That'd be the distance. And what about the angle there? So we have a right angled triangle. You would use right angled trig, SOHCAHTOA. You've got the opposite and the adjacent side, and you'd work out the angle using tan. Well, vectors can help us to work out these sorts of problems. That if we have a starting point here and a finishing point over here, we've got 2 resulting vectors. We've got one that was 4 kilometres going east and another vector that was 2 kilometres going south. So that's got direction and distance, and that helps us to work out the end point. So that's sort of where we're heading. So imagine you had an object. Again, we had the runner. Imagine this is a person or an object, and it's being moved to the right, and we'll call that A, so the vector of A. And then vertically, it's also being pulled up. We'll call that a vector of B. And so we're asked, what would be the resultant force acting on this block? So imagine something's it doesn't just go move to the, which way, this for you, the right, and then wait, and then it goes up. Both of those forces are acting on it at the same time. So imagine how that's going to be pulled along. We have to add the vectors A and B together to find the resulting force. And to do that, one vector is placed at the end of the other. So we're going to get into this in a bit more detail, that you would take the arrowhead of where you've ended on A and you would place the beginning of the next arrow at that end. And you would get that diagonal vector. And we'd call that A plus B. And that would be our final one. Okay, so imagine 3 points here. If we had P, Q and R, imagine they could be towns if you like. So P to Q, imagine that, plus Q to R. What's that the same as? Could you do it in one move? So P to Q and then Q to R. Notice the one arrow ends and the next one begins. And that would be the same as from P to R. And that's how we write that there, capital letters with the arrow on top. So P to Q plus Q to R. Notice that the middle letters are the same. One way you might like to remember this is, I'm sure there's some games out there where you've got like coloured marbles or something and you have to match them to get, once they're all next to each other, they disappear. Imagine it's like that. You've got to get the middle letters matching next to each other for vector addition or subtraction to work. Okay, the 0 vector. So it's a vector with length, what? 0. Think about it this way, if you have the vector A and you're adding on the vector 0, it's the same as having the 0 vector and adding on the vector A. What would our result be? A. So we've essentially added on nothing. It might seem trivial, but this will come in handy at some points. What about this one? Vector A, and you're adding on where you subtract off A, so the negative of that. That is the same as if you write it around the other way. What would the resulting vector be then? Let's have a think of that visually. So if we have a vector here, and we call that A, then this would be negative A, so it's the same magnitude, but in the opposite direction, so still running parallel. How do you add those? Essentially, merge them on top of each other. So remember, we've got one arrow and we go to the end of that, that way, doesn't matter, and then we come back the other way. So where are we? We've ended up where we started. And so putting that here, that is the 0 vector. All right, given vectors A and B shown, we have to construct A plus B. So the technique here is you've got vector A and the arrowhead is there, that's where A has ended. You take B, the start of B, and you move it to be at the start of A, and it'll have its direction and magnitude. So thinking about B, it goes down 2 and across 4. So from the end of A here, we're going down 2 and across 4. And so that's what that would look like. And then to draw A plus B, as in one go, you connect the beginning of A to the end of B. And for a single vector, which is equal to, so looking at this diagram here, we need one vector that's the same as B to C, so we've got that there, and then C to A. So where did we start? We started at B, we went to C, and we're ending at A. So we need to write one vector that is the equivalent of that. And I'm sure you can see that that would be B to A. So for our first one, we're going to write B to A, capital letters, and an arrow. Excellent. The second one, B. Okay, so B to A is where we start, B to A, and then we're going from A to E, and then from E to C. So we need to write one vector that is the equivalent of that path. Notice we started at B and we ended at C. So we're going to write BC, capital letters with an arrow. A to B then B to C, and C to A. Interesting here. Notice first of all that all of those middle letters match, the B's and the B's match, and the C and the C match. So we went A, B, C, and back to A. What could we write that's the equivalent of starting there? One way you could write it is the place that you started was A and the place that you ended was A. So that's the vector A to A, which is the equivalent of the 0 vector. And D, we have A to B, so A to B, then B to C, C to D, and D to E. And we want to write one vector that's the equivalent of that whole path. So we just want from A to E. And so we write that A to E, capital letters with an arrow going over both of them. Excellent. Okay, and the next one in this series, we'll look at vector subtraction and vector equations. Thank you.